Welcome to this session on CCNA tutorial, Network Fundamentals. This video is aligned with Cisco's official CCNA 200-301 exam blueprint and is designed to guide you step-by-step toward certification success. Section 1.13, Switching Concepts. In this section, we're going to break down some of the most important switching concepts you'll use throughout the CCNA and in real networks. We'll take a clear, step-by-step look at how switches actually operate at Layer 2. Things like how they forward traffic, how they learn MAC addresses, how they deal with broadcasts, and how they separate traffic using VLANs. The goal here isn't just to memorize terms, but to really understand the logic behind switching so the configuration part becomes much easier. By the end of this section, you'll have a solid foundation that everything else builds on. When we look at how switches operate, everything begins with the Ethernet frame. This is the basic data unit traveling across the LAN. The switch isn't analyzing IP addresses yet. It's focused on specific Layer 2 fields inside the frame, like the source MAC, destination MAC, and the type/length field. Frames also have a minimum and maximum size and include an FCS at the end, which allows the switch to detect errors. If the FCS doesn't match, the frame is simply dropped. Understanding this structure helps explain why switches forward some frames, filter others, and flood the rest. In Ethernet, every frame you see falls into one of three traffic types: unicast, broadcast, or multicast. Unicast traffic is straightforward. It's one device sending directly to another, and the switch uses its MAC table to forward it. Broadcast is delivered to every device on the same network segment, and you see it in things like ARP or DHCP. Multicast is meant for a group of devices, such as streaming or discovery protocols. Early on, switches treat multicast a lot like broadcast until additional features refine it. Knowing these three types helps you predict how the switch will forward each frame. A collision domain is simply the area where two devices could transmit at the same time and interfere with each other. This was common with hubs, where everyone shared the same medium. Modern switches change that completely by giving each port its own collision domain. That means devices can send and receive independently, especially when operating in full duplex. If you ever see late collisions or errors, that often points to a duplex mismatch or cable issue. Understanding collision domains is key to seeing how switches improve performance compared to old shared media networks. Let's imagine a small network that originally used a hub. With the hub, all devices shared one big collision domain, so whenever two PCs transmitted at the same time, their signals collided and they had to retry. After replacing the hub with a switch, each device now connects to its own dedicated port. That immediately eliminates collisions and allows full duplex operation. Traffic on one port no longer interferes with traffic on another. This simple upgrade dramatically increases reliability and overall network performance. A broadcast domain defines how far a broadcast frame can travel. When one device sends something like an ARP request, every other device in the same broadcast domain receives it. Switches forward these broadcasts out every port except the one they arrived on. Routers, on the other hand, stop broadcasts. They don't pass them along, which creates the broadcast boundary. Because every device has to process each broadcast, too many broadcasts can affect performance. Unknown unicast traffic also stays within this same boundary until the switch learns where the destination lives. A VLAN creates a logical separation inside a switch, allowing you to divide one physical network into multiple independent Layer 2 networks. Devices in the same VLAN share a broadcast domain, while devices in different VLANs are fully isolated unless routing is involved. VLANs help with organization, security, and controlling broadcast traffic. Each VLAN has an ID, and a switch can support many VLANs at once. When VLANs span multiple switches, tagging keeps their traffic separate. This is the foundation of modern network segmentation. Picture a switch that has three different VLANs defined. When PCA in VLAN 10 sends an ARP request, only devices in that same VLAN receive it. In this case, just PCB. Devices in VLAN 20 or VLAN 30 never see that broadcast. The same happens when PCC in VLAN 20 sends a DHCP discover. Only devices in that VLAN respond. This setup keeps each group of devices isolated and prevents unnecessary broadcasts from crossing into sections of the network where they don't belong. The MAC address table is the switch's internal map of where devices are located. It keeps track of which MAC address is reachable out of which interface, so the switch can forward frames directly without flooding the network. This table constantly updates as devices move or reconnect, and it lives in high-speed hardware, so lookups are extremely fast. Without this table, the switch would have to flood nearly everything, so it's a critical part of efficient Layer 2 switching. MAC learning is how a switch builds its MAC address table. Every time it receives a frame, it looks at the source MAC and records which port it came from. This allows the switch to map devices to ports and forward traffic efficiently. Learning happens per network segment, and if a device moves, the entry gets updated automatically. Once the switch knows where devices are, it doesn't need to flood traffic anymore. It can forward frames directly. This dynamic learning process keeps switching fast and accurate. Imagine a switch with several devices connected, but an empty MAC table. When PC1 sends traffic to PC2, the switch sees the frame on its incoming port, learns PC1's MAC, and records it. Because it doesn't yet know where PC2 is, it floods the frame to the other ports in the same segment. PC2 receives it and replies, and that reply allows the switch to learn PC2's MAC as well. From that moment on, traffic between PC1 and PC2 is sent directly between their ports with no more flooding. Frame switching is the core function of a switch. When a frame arrives, the switch checks the destination MAC and looks it up in the MAC table. If there's a match, it forwards the frame only to that specific port. If the destination happens to be on the same port the frame came from, the switch filters it out because forwarding it would be pointless. But if the switch doesn't have an entry, meaning it doesn't yet know where that MAC address lives, it floods the frame. This forward, filter, or flood logic is the foundation of switching. Switching methods describe how quickly a switch processes frames before forwarding them. Store and forward is the most common. The switch receives the entire frame, checks the FCS, and forwards only if it's clean. That makes it reliable and ideal for modern networks. Cut-through is faster because the switch starts forwarding as soon as it reads the destination MAC, but it may forward corrupted frames. Fragment-free is a hybrid that waits for the first 64 bytes to avoid partial collisions. Understanding these methods helps explain the balance between speed and accuracy. Frame flooding happens when the switch doesn't know where the destination device is yet. For example, when a device connects for the first time and no MAC entry exists, the switch sends that frame out every port in the same network segment except the one it came in on. Broadcast frames are always flooded, and multicast frames are initially treated the same way. Once the switch learns the MAC address and associates it with a port, flooding stops and the frame is forwarded directly. Flooding is normal, but too much of it can indicate misconfigurations or network issues. MAC aging keeps the MAC table clean and prevents outdated information from causing issues. Each learned MAC entry has a timer, usually around 300 seconds, and the timer resets every time the switch sees traffic from that device. If a device goes silent or disconnects, its entry eventually expires and the switch forgets it. This frees up space and ensures that if the device reconnects somewhere else, the switch learns its new location correctly. Static entries, on the other hand, never age out. Static and sticky MAC addresses are ways to give a switch more control over which devices are allowed on a specific port. A static MAC is manually assigned and never ages out, making it useful for devices that shouldn't move. Sticky MAC starts as a normal learned address, but becomes fixed to the port after it's learned. Both methods help prevent unauthorized devices from connecting or swapping cables and provide more stable behavior on sensitive ports. MAC flapping happens when a switch sees the same MAC address appearing on different ports. This usually means the device is connected in two places, or there's a loop or misbehaving device on the network. The switch keeps updating the MAC table back and forth, which causes unstable forwarding and can lead to excessive flooding. It's a common symptom of wiring mistakes or accidental loops, and most switches will log a warning when it happens. A MAC table overflow occurs when the switch's MAC address table becomes completely full. This can happen if too many new MAC addresses show up at once, or in worst-case scenarios, through a malicious MAC flooding attack. When the table is full, the switch can't learn new MACs and begins treating unknown unicast traffic as broadcasts. That increases flooding, impacts performance, and can even expose traffic to unintended devices. It highlights why aging and table management are so important. This brings together the core ideas behind Layer 2 switching. We covered how Ethernet frames are structured, how unicast, broadcast, and multicast traffic behave, and how collision and broadcast domains shape the network. We also explored MAC learning, the MAC address table, switching decisions, flooding, and aging. Finally, we looked at extended behaviors like sticky MACs, flapping, and table overflow. With these fundamentals in place, you're ready to move into the configuration side of things and see how all of this works on real devices. Before moving on, take a quiz to test your understanding. Quizzes, summaries, and slides are available on ccna.academy. If you have any questions, leave a comment below and I'll be happy to help. In the next part of the course, we'll move from concepts to hands-on configuration. We'll start working with VLANs, verify access and trunk ports, and set up inter-VLAN communication so different segments can talk to each other. This is where the theory you've learned becomes practical. If you're comfortable with everything from this section, you're ready to continue. And if you need a quick refresher, feel free to revisit the video for this entire module.